Hey, what's up, guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127 Random Signals. In this lecturette, I'm going to show you how to perform hypothesis testing when we are comparing two different populations. Now, this kind of studies arise quite frequently in science and engineering, specifically when you perform some sort of a treatment on your existing data or existing experiment, and then you would like to find out whether the treatment on this experiment has worked or not. For example, let's say that I'm quite interested in health and fitness and I'm quite passionate about a particular exercise movement, the squat. Further, assume that I have been performing squats, but I have not been consuming any protein powder or I have not been consuming any supplements to help me recover from the squats. So I may have certain number of squat personal record numbers, or commonly referred to in health and fitness as squat PRs. Let's say that I decide at one point that I need to consume some amount of supplementation in order to help me increase the squat. And let's say that I start performing or start taking the supplements in, and then I would record how my squats go. So the squat numbers before the supplementation happens to be a set or a sample from a population of all the squat values that I may ever get without the supplementation, whereas the squat numbers after taking the supplementation is your set Y or sample Y, which is extracted from another population, which includes all my squat numbers with supplementation. So in this way, I'm trying to test whether or not supplementation in my diet helps me improve my squat numbers or not. In this way, I'm actually comparing two different population means. One population mean corresponds to squat numbers without supplementation, whereas the other population mean correspond to the squat number when taking supplementation. So in order to perform such a hypothesis testing, there's much more rigorous mathematical analysis which involves the calculation of pooled sample variance. I'm not going to show you those deep mathematical concepts because I think it's a little bit out of the scope. But nonetheless, I would like for you guys to be able to use the statistical package R to perform such studies, because let's be honest, such studies are much more useful and much more interesting in order to find whether or not, hey, you know what, a treatment has worked or not. So let's say that you have two data samples, let's say X and Y, and they come from the same subject before and after the treatment respectively. In such a case, in order to compare their population mean, we perform the same t-test, and the first argument is the data X, which is essentially in the form of a vector. The second argument is data Y, which is again the vector. And the alternative that I'm going to choose here will be either two-sided, less, or greater. I'm going to choose alternative as two-sided if I would like to compare the, or if I would like to evaluate the alternative hypothesis that X is not equal to Y, or mean of X is not equal to Y. I'll perform alternative as less if I would like to test the alternate hypothesis that mean of X is less than mean of Y, and I'll do alternative greater if I would like to test my alternate hypothesis as mean of X, mu, or rather mu of X is greater than mu of Y. Because X and Y are coming from the same subject, I am going to set paired as true. Variance, typically I would recommend that you assume that both X and Y come from two different populations that have different variances, and the confidence level here is 95%. This is quite standard method to use the particular confidence level value. So this is paired t-test where I'm evaluating the effects of a treatment on the same subject. So for example, if I would like to compare my squat numbers before and after supplementation, because this test is conducted on the same subject, aka Dr. Palipuram, I'm going to construct, or I'm rather going to consider a paired t-test. However, if X and Y, if they tend to come from different independent subjects, then I'm going to perform an unpaired t-test where the value of paired is going to be equal to false. For example, let's say that I'm trying to compare my squat numbers with my buddy's squat number. So here I would compare the two samples using an unpaired t-test. Unpaired t-tests are also useful for comparing two different samples, maybe from the same population, if they do not have the same size as well. So that's the general methodology of choosing either paired t-test or an unpaired t-test. If the subject remains the same, then it's going to be a paired t-test. If the subject is going to be different, or rather if X and Y come from different subjects, then it's going to be an unpaired t-test. So let's take an example of a real world situation here, and I'm going to give you an actual real world data, aka my teaching evaluations. So here in the University of the Pacific, I have worked for 5 years, and somewhere down in the middle, at my year 2.5, I was evaluated for my teaching. And prior to evaluation of my teaching methodology was quite lecture based. I used to deliver the lecture hoping that students are listening fine, and then they would give me their own teaching evaluations. After my mid point, or rather after 2.5 years at University of the Pacific, I analyzed my teaching methodology, and I found that, hey, you know what, if I were to engage students a little bit more with a lot of problems in the class, I can possibly help them understand difficult concepts even more. So I introduced this new treatment in my teaching, and that is, in my traditional teaching, I sprinkled in-class participation problems that students will solve along with their peers so that they remain engaged and they are able to understand difficult concepts. It helps me to keep students engaged. If I find that the students' concentration is going down in the class, I immediately follow up with a problem with the hopes that the students' concentration is going to come back. So I performed this kind of a treatment, so to speak. So let me define what the problem is. So I have some teaching evals before 2.5 years, or rather from 0 to 2.5 years of my career, where I do lecture-based classes with minimum problems in class, versus teaching evals from 2.5 years until now, where I do lecture plus a lot of problems in class. So I would like to find out whether including this lot of problems in the class has affected my ability to explain difficult topics. So what I did for this particular example is I pulled my teaching evaluations right from 2015 until this point 2020, and I constructed data for teaching evals based on lecture-based classes alone, and teaching evals based on lecture as well as a lot of problems inside of the class. And let me show you how I prepared the data for my analysis in R. Okay, my apologies, that's my little daughter, little girl, who is protesting as her diapers are being changed. Okay, so let me show you the data. So the data is saved in a nice CSV file, comma separated file, and R software likes the comma separated files a lot because R is capable of reading the individual columns in the comma separated file in addition to identifying the header of each of these columns. So here's my comma separated file. So these are my average points for ability to explain difficult concepts. So the very first column that you see are my numbers from different courses before my pre-tenure evaluation at the year 2.5 of my stay here at University of the Pacific. And the second column that you see here is my ability to explain difficult concepts rating by my students after I introduced this technique of including a lot of in-class participation problems to keep students motivated and interested. So I'm going to show you how to input this comma separated file in our software and perform the analysis. When you perform statistical analysis, usually the very first item is to prepare the data and for appropriate analysis. Believe it or not, data scientists spend a lot of time cleaning and sanitizing their data before they actually perform data analysis. Data analysis sometimes is the easier part. data preparation and sanitization is the first task. So this is the first task that I did. I prepared a CSV file, which is essentially my data preparation for this experiment. So let me open the R software, and I'm going to show you how to read in this CSV file. In order to read a CSV file in R, you use a function called read CSV. So I'll create an object variable, say A, and use this function read.csv. If the file is present in the same path as that of R, so I will just say, okay, I think forgot the name of the file. Okay, explain.csv. So explain.csv. You can also enter the complete path to the file. That will always work. After you execute this command, just make sure, excuse me, my apologies. Okay, just make sure that A has been properly read or not. Sometimes R is not, excuse me, okay, pollen allergies, I guess. So just ensure that A has been properly read. So I just type A in my R terminal, and I find that I have those two columns, pre-tenure evaluation, ability to explain concepts, and post. So the pre one is the one before I introduce the concept of in-class participation problems, and the post one is the evaluations after the treatment. In R, I can extract these individual variables into my own variable. So let's say that I declare a variable pre. Let me call it capital P pre, and I can set it to $pre. So this $sign is essentially a kind of an operator that helps you access different members of this object A. So this is quite similar to C or C++, where you have the dot operator to access different members of a structure. So I extract pre as $pre. As a sanity check, I'll type pre in my terminal and find that I have indeed read it properly. Now I will read in post. So post is equal to $post. Let me make a deliberate error here, and that deliberate error is instead of entering small p ost, I'll enter capital P ost. R has not given me any error. When I try to see whether post was read in properly or not, I find it null. So please make sure after you read the values into different variables inside of R, make sure to print them out by just typing the variable's name in the R's terminal in order to, as a sanity check essentially. So I'll correct that mistake of mine and change that to small lowercase p. So now post is proper post. So pre is my variable x essentially. Let me say x is equal to pre and y is equal to post. So x and y are pre and post respectively. So these two are the samples from two different populations now, and I need to compare whether they are different or not. So in order to find out whether they are different or not, my alternative hypothesis H0 or HA will be mean of x is not equal to mean of y. So that's my alternative hypothesis. My null hypothesis will be mean of x is equal to the mean of y. Usually you specify H0 first and alternative hypothesis next. Because your alternative hypothesis is not equal, the mean of x can be either greater than mean of y or it can be less than mean of y. Therefore, it's a two-sided test. So I'll perform my two-sided test like this using the t.test function. So t.test x, y. My alternative is two-sided. It has to be in double quotes. So two-sided paired is going to be equal to true. Paired is going to be equal to true because it's coming from the same subject, aka Professor Pylipuram. I will assume that the variances of these two different populations are not equal. So variance.equal is false. and the confidence level I will include as 0.95. So here the value of alpha here is 0.05, which is the error of incorrectly rejecting H naught. So let's see what t.test function gives us. So the t.test function gave us the test statistic. So it's going to compute the test statistic, which you typically do using hand and or pencil and paper, but instead we are going to rely on our software. So our software has given us the value of the test statistic as negative 2.65, and the probability associated with it is 0.02, or rather 2.8%. So here 2.8% is the, let me start over one more time. I think I did not mention that pound is for comments in R. So in this case, the p-value is 2.8%. So that 2.8% is the chance of incorrectly rejecting H naught. So if I reject H naught, the probability that I am wrong is 2.8%, which is less than threshold, 2.5%. Because of this, I can safely reject H naught and go with HA. So my statement will be as follows. My conclusion will be as follows. There is sufficient statistical evidence to suggest that the average rating for the ability to explain difficult concepts is different than different post tenure or is different after including class problems versus lecture only classes. So that's great. So there has been, it actually tells me as a professor and as a teacher that the new teaching methodology that I have adopted some 3 years ago, or approximately 3 years ago, has indeed changed my ratings. Now I have to find out whether it has changed it positively or negatively. So I need to find out whether X is less than Y or whether it is greater than Y. Y here is my evaluation after post tenure, or after including this new concept of including in-class participation problem. So now let us test whether or not my ability to explain difficult concepts has gone up after this new treatment or not. So I need to find out whether X is less than Y. So my null hypothesis will be mean of X. To be very frank, it should be ability to explain difficult concepts pre and post, or ability to explain difficult concepts has not changed, essentially meaning that mean of X is equal to mean of Y, so there's no change. The alternative hypothesis will be mean of X is less than mean of Y, which is ability to explain difficult concepts has improved after including in-class problems. And for this, I'm going to perform a less alternative. So I'm going to use the less alternative here because I want to evaluate mean of X is less than mean of Y. So I'm going to use less alternative. Okay, so I'm going to re-input the function t.test. X, Y alternative is going to be less because I would like to see whether or not x is mean of x, the true mean of x is less than the true mean of y or not. Paired is equal to true because I am the subject. Variance dot equal is false. I have reasonable faith that the two populations will have different variances, and the confidence interval that I choose, confidence level, is equal to 0.95. So when I perform this test, the statistic value is negative 2.65 and the p-value is 0.015, which is 1.5%. So 1.5% is the probability of incorrectly rejecting H naught. So if I reject H naught, the probability that I am wrong is 1.5%. So reject H naught. So reject H naught. So I'm going to reject the H naught, which is so I'm going to reject the H naught here. Okay, so I'm going to reject H naught and I'm going to go with the alternative hypothesis H of A, which is mean of X is less than mean of Y, which implies that there is sufficient statistical evidence to suggest that after including in-class problems, the ability to explain difficult concepts Y is more than the rating for lecture only method X. Okay, I should have included a pound sign here. So there you go, guys. So here's a real life example of how one uses statistics. I actively use statistics even to evaluate my teachings. So I find out whether I value your teaching evaluations to the point that I conduct regular statistical analysis to find out if the different categories in which a professor is typically evaluated, if I am faring well or not. If I find that my teaching evaluations in any of the categories is going down, I immediately address that aspect. So I'm pretty sure other professors do the same because we are committed to perform the best possible education for you guys at University of the Pacific. Okay. All right. So that's how we compare the population means. Now let's take a look into another problem, and for this problem, I'm going to just solve part A here. So let's say that I have a machine, and I apply three kinds of optimizations on that machine for a particular